Hello, welcome to Lesson 5 of Module 1 from my new course on Networking Fundamentals. This module will teach you everything you need to understand how data flows through the internet. In this lesson, we'll be picking apart routers, and we'll show you everything routers do to facilitate communication between networks. Before watching this lesson, it is recommended to have watched the prior lessons in this series. In Lesson 1, we discussed the concept of networks. We defined them as a logical grouping of hosts. We mentioned that each network has its own IP address space, and each host has an IP address in that network's IP address space. We also defined switching as the process of moving data within networks, and then we define routing as the process of moving data between networks. A router, which is going to be the focus of today's lesson, is simply a device whose primary purpose is routing. Then, in Lesson 2, we discussed the OSI model. We used this illustration to discuss the interaction of Layer 2 and Layer 3. We showed you that for this host to send some data to this host, it would start by adding a Layer 3 header, which included a source and destination IP address of the two endpoints of the conversation. Then a new Layer 2 header is added to facilitate each hop along the path between the two endpoints. All of this was discussed in detail in Lesson 2. Then, in Lesson 3, we focused on hosts, and we showed you everything hosts do when speaking to other hosts. We first showed you everything hosts do to speak to other hosts in the same network, regardless of how they are connected. Then we showed you everything hosts do to speak to other hosts in foreign networks, regardless of how they are connected. Both of these illustrations allowed us to discuss ARP, or the Address Resolution Protocol, and show you ARP's role in internet communication. All of this is the prerequisite knowledge you'll need to fully understand this lesson. If any of these concepts are unfamiliar to you, please check out the first 3 lessons of this course. There are links in the description. In this lesson, we're going to be focusing on routers, and we're going to show you everything that routers do to move data across the internet. Here is a network with 2 hosts. Each of these hosts have a MAC address and is configured with an IP address in this network's IP address space. For these hosts to speak to each other, they would have to be connected to a switch, and this switch will facilitate all the communication within this network. But for these hosts to speak to a foreign network, we would have to add a router. Now, routers are also connected to a network, which means routers, just like hosts, also have an IP address and a MAC address, and all the rules of Layer 2 and Layer 3 that we've discussed prior still apply in order for these hosts to speak to this router. Now, in order to keep things simple and reduce the variables, since we've already talked about switches in the last lesson, we're going to leave switches out of this lesson entirely. But everything we discussed about how switches work still apply, so feel free to watch Lesson 4 if you want to understand how that works. In this lesson, we're just going to be focusing on routers. Now, if routers have an IP address and a MAC address, just like hosts, what then is the real difference between a router and a host? Well, my favorite definition for routers and hosts actually comes from the IPv6 RFC. If you're unfamiliar with RFCs, they stand for Requests for Comments, and they are the type of document that define internet standards. In fact, if you're ever in a nerd argument with someone and you are debating about how something in the networking world works, whoever can quote the RFC always wins, because the RFC is literally the instructions that were used to build the internet. In any case, RFC 2460 is the IPv6 RFC, but it provides a useful definition for hosts and routers that also applies to IPv4. The RFC defines a node as anything which implements IP, or anything with an IP address. It then defines a router as any node that forwards packets not addressed to itself, which leaves the definition of a host to be a node that is simply not a router. So the real difference between a router and a host is that routers forward packets not destined to themselves. That is how they are different from hosts. For example, if this packet were to magically appear on this network and arrive on host D would take a look at the destination IP address and realize that it is not itself and would simply drop this packet. But if this packet were to arrive on router 1, Router 1 would recognize that it is not destined to itself, but would still try and deliver this packet to the appropriate destination. That is how hosts and routers are different. Now, of course, for router 1 to actually forward packets not destined to itself, there has to be another network that exists. So let's go ahead and add another network to our topology. A moment ago, we said that routers have an IP address and a MAC address. That, in fact, is what is meant by router 1 being connected to a particular network. But now that we have another network, router 1 is going to need another IP address and MAC address in order to be connected to the new network. Here, we've configured router 1 with the IP address 10.055.1, and that is what officially connects router 1 to this new network. In order to accomplish this goal, routers must maintain a map of all networks that they know about. This map is known as the routing table. Inside a routing table is what's known as routes, and each route is merely a set of instructions for how to reach a specific network. For our topology over here, there are two networks, 10.055 and 10.044. And router 1 is going to have a route correlating to each of those networks. The first route will tell router 1 that to reach anything in the 10.055.x network, router 1 should send that packet out the left interface. And the second route will tell router 1 that to reach anything in the 10.044 network, router 1 should use its right interface. Normally, the interfaces of the router would be slightly more technical, something like FA01 or GIG02 or ETH0 or ETH3. But to keep things simple, in this presentation, we're just going to use left and right to indicate the left interface or the right interface of the router. So that is a basic rundown of routers and specifically the routing table. But the routing table is actually a very important concept in networking. In fact, a large part of a network engineer's job is to ensure that every router has the proper routes in its routing table in order to move packets through a network. Therefore, we're going to spend a bit more time digging into the concept of a routing table and discussing the different methods that routes are learned. There are three ways that routes can be populated in a routing table. The first method is what's known as directly connected. A directly connected route exists for every network that a router is directly attached to. In the case of R1, R1 is directly connected to two different networks, and therefore will have two different directly connected routes in its routing table. The first one, telling R1 that the 10.055 network exists out the left interface, and the second one, telling R1 that the 10.044 network exists out the right interface. Now, if this is familiar to you, it's because it's the exact same thing we had a moment ago when we looked at R1's routing table, except this is a more formal way of displaying a route. Now let's add another network and another router to our topology. Here we have R2 in between the 10.066 network and the 10.055 network. Each router is going to maintain its own routing table, which means router 2 has its own routing table that is independent from router 1's. In each case, the routing table is a map of every network that router knows about. Just like before with R1, in order to attach R1 to the 10.044 and the 10.055 network, we had to configure an IP address in each of those networks. The same thing will apply with R2. For R2 to be attached to the 10.055 network, we're going to have to plug R2 in and then configure an IP address in this network. In this case, we've configured the IP address 10.055.2. This created a directly connected route in R2's routing table, telling R2 that the existence of the 10.055 network exists out R2's right interface. In the same way, as soon as we configure this IP address on R2's left interface, this adds a new directly connected route to R2's routing table, telling R2 that the 10.066 network exists out R2's left interface. Each of these routers will now use their own routing table to move packets through this topology. For example, if this packet shows up from host C with a destination IP address of 10.055.8, that's host B's IP address, R2 will take a look at its routing table to determine that the 10.055 network exists out the right interface and will forward that packet along. But what happens if host C now sends this packet? Well, this packet has a destination IP address of 10.044.9. That's host A's IP address. When router 2 takes a look at its routing table, it's not going to find an entry for the 10044 network. At this point, router 2 does not know how to get to the 10044 network, which unfortunately means router 2 is simply going to drop that packet. When a router receives a packet with a destination IP address it doesn't know how to get to, the packet is going to be dropped. Remember, from the perspective of each router, the routing table is a map of every network that exists. And at this point in time, router 2 does not know that the 10044 network exists. And since R2 is not directly attached to the 10044 network, it's not going to have a directly connected route in order to get to the 10044 network. But lucky for us, there are still two other methods that exist for how a routing table can be populated with routes. The second method to populate a routing table is what's known as a static route. A static route exists anytime an administrator manually provides instructions to a router about the location of a particular network. For example, I can log into router 2 and configure it with a static route, telling router 2 that anytime it wants to reach the 10044 network, it should send that packet to the 10055.1 IP address, which is router 1's IP address. Now, if router 2 receives this packet from host C, it'll take a look at the destination IP address, find a match in its routing table, and forward that packet along to the next router in the path, in this case R1. R1 will then take a look at its routing table and determine that this packet should be sent out the right interface where it'll arrive on host A. So that's an example of a static route. But what happens if host A responds? This response is going to have a destination IP address of 10.066.7, which is host C's IP address. And when R1 receives this response, it's going to take a look at its routing table, and at the moment, router 1 does not know how to deliver this packet. So normally, router 1 would just drop this packet. But just like we use a static route to tell R2 about the 10044 network, we can also use a static route to tell R1 about the 10066 network. This static route would tell R1 that the 10066 network can be reached by going to the 10.055.2 IP address, which is router 2's IP address. With this static route, router 1 now has instructions on what to do with that packet, which is to send it to R2. R2 will then take a look at its routing table to determine that the 10.066 network is out the left interface, where it'll deliver the packet to host C. So notice we were able to use static routes to tell both of these routers about the networks that they didn't know about because they weren't directly attached to them. The last way that a routing table can be populated is what's known as dynamic routes. A dynamic route is very similar to a static route, except instead of an administrator telling the router how to get to a particular network, a dynamic route is the routers automatically talking to each other and sharing information that they know in order to tell each other how to get to the networks that they can get to. For example, if we got rid of these static routes and instead told R1 and R2 to do dynamic routing amongst each other, R1 would share with R2 that R1 knows about the 10.055 and the 10.044 network. R2 would say, oh, I already know about the 10.055 network, but I don't know about the 10.044 network. Anything R2 gets destined to the 10.044 network, it's just going to send to R1. In the same way, R2 will tell R1 that it knows about the 10.066 and 10.055 networks, and R1 will learn that anything destined to the 10.066 network should simply be sent to R2. Now notice that the content of the actual dynamic route is identical to what it was with the static route. The only difference is how it was learned. If an administrator logged into the router and manually told the router how to get to a particular network, that is a static route. And if the routers automatically talked to each other and told each other of the networks that they know about, that is a dynamic route. Now the exact method that the routers will use to talk to each other to exchange these dynamic routes is governed by what's known as different dynamic routing protocols. There's a bunch of them that exist. The most common ones are right here. Each of these are simply different ways and different communication protocols that the routers will use to share routes with one another. Each of these differ insofar as how often networks are shared with one another, how they discover each other's presence, what sort of information is included with each route, and how much control you have over the routes that are received or sent. The inner workings of each of these is pretty fascinating and a large part of the network engineering career field, but unfortunately, the details of how each of these work is outside the scope of this particular module. The main takeaway of this lesson is simply that dynamic routing protocols are what are used between the routers in order to share these dynamic routes. Either way, that wraps up our discussion of the 3 ways that routing tables can be populated. And that also wraps up our discussion on routers. The main takeaways for this lesson is understanding that routers need an IP address and a MAC address for each network that they are connected to, and that routers maintain routing tables, which are a map of every network that the router knows about, and those routing tables are populated via 3 different methods. In part 2 of this lesson, I'm going to show you every single step that occurs for a packet to get from host A all the way to host C, and for host C to respond, sending a packet all the way back to host A. But that's it for this lesson. The main takeaways for this lesson are on your slide right now. I hope you enjoyed this video. I want to thank you for watching, and we'll see you in the next one. Hey YouTube, I hope you enjoyed that free lesson. I'm releasing this content for free to see how much interest there would be in a full Networking Fundamentals course taught in the same practical networking style. If you want the full course to be created, you have to help me out by spreading the word about this free module. If this content gets enough attention, I will definitely create the full course based upon your suggestions for what you want in a Networking Fundamentals course. Besides, I'm sure you know someone that would also benefit from learning how data flows through the internet, so you'd be helping them by sharing these videos. You could also further help me out with the YouTube algorithm by liking, subscribing, and leaving a comment below. I would appreciate it greatly, and I read and respond to every comment. Otherwise, feel free to join fellow learners and fans of practical networking on Discord. The invite is available at pracnet.net/discord. Thank you for watching, and we'll see you in the next video.